work calculation is somewhat um, related in physics with the conservation of energy. So, for example, if this is suppose this is a building, and you have some sort of lifting machine that you can lift the water directly, certain amount of water, one body of water, bucket, directly up in here, or there's a worker going around the staircase, going to the top of this building like this. Sorry about this terrible picture, but there's a staircase, and this guy is actually holding this water and going around like this. And the work done along the path of this one. Suppose this is now iced water and drilled water, and there's a path, and you're actually pushing this water along this path, just like I was doing in that advanced problem. Not actually carrying this water around the staircase. It's a bid, and you're pushing this water along this one. Then probably you can imagine that the force that required to push along that path is the force required to do that is less than actually pushing it directly upward. That makes sense, right? You need less force to push this along this path than pushing it directly upward. I was practicing jumping rope yesterday, and I thought jogging it forward gives you a little less than 10 degree of pushing it forward. And when you're jumping rope, you're actually dealing with the forces, and you quickly get tired. All the muscles and everything very quickly get tired. Enormous. So you can actually use the cosine value to compute the ratio of jumping rope versus actually running it forward, and that is actually drastic difference is there. But this conservation of energy kind of stuff allows you to conclude like this work you're doing from here to there is the same as work you're going around in here. Less force and longer distance multiplied versus shorter distance and harder force multiplied. That's a qualitative description, but exactly that a way of calculating gives you the exact same amount. So it doesn't matter how you go around, and it's all that matters where you begin and where you ended. And if the force field, the gravitational force field, allows you to conclude something like this, that force field is called conservative vector field. You probably heard about it, and maybe you will hear later in the physics and calculus 3. All right? So, and here, you can think about it like this. Why are you making it so difficult? Here's a body of water, and don't slice it. Just take the entire thing, just lift it up. And then it should be the same work if the work definition is correct, right? But if this is a location, if this is the height that you were lifting this one up, it's unclear where this thing ends because the size of this body is huge. So as soon as we touch that, the C position or as it passes, that's unclear. So Newton come up with brilliant idea that is prevailing in his many of this theory, even in these universal gravitation law. The huge body of star, and when we are applying the universal gravitation, what is the point that we have to apply? You can't apply to this entire mass of the body. So here's his idea. Think about, suppose you're actually, this is now is iced water, this is actually, and then you can't really compress it, but replace it with heavy ball, metal ball, whose mass is actually the same as that. Maybe uranium ball, whatever. It's very, very tiny ball, so its actual volume is almost negligible, but its mass is enormous, so it's actually the same as that. So when you're lifting this entire thing, you're dealing with exactly the same body and the mass of the water, right? So he thought is everything that matters is the mass, not what is made out of in the gravitational and the thing that you're dealing with. So we're going to pull this one up like that, and that must be the same work calculation, right? So that was the idea, but it's unclear where to locate this one. So figuring out where the location of this ball, that gives you the same amount of work as you're doing after you slice the water and lifting individual pieces of water. So let's say that was some location Y star in there, right? And replace the entire body of water into a smaller piece with the same mass. And lifting this one up all the way to the C minus Y star. whatever the location is. So to him, that location is important, and he obtains this same result and over in different interpretation, and everybody realized, and he himself realized that this must be the important notion that has to be addressed. So something can be something important about the rigid body that is coming. All right. So what is the mass in here? If you have to calculate this mass, it's a uniform amount of water. So it's the volume. So it goes like this. The mass of this thing is really. Let me do it this way. What is the volume of this thing? How do you calculate the volume? You know the cross-sectional area, right? And if you integrate from y equals a to b, you get the entire volume, right? And you multiply. What do you multiply? Density and the gravitational force, and you get the weight, and then this is the force that is applied to that. Does that make sense? So that's the volume multiplied by density, pi by gravitational acceleration. The whole thing is the weight that you're dealing with when you lift this ball, right? So what is the distance we're going to lift this up? So that's going to be y c minus y star. The work, maybe w prime is different work, is a c minus y star, and I'm going to put that constant inside, a to b, g and rho, ay, and dy. So one difference is the c minus y was inside before. This time there's a constant y star, and all you have to do is just integrate this ay thing pretty much to the c minus y star. That must be the same as the earlier one we calculated. W equals g rho a to b ay c minus y dy. These two things must be the same. Okay? So that's the idea. If the work and definition is defined correctly, these two things must be the same. So if you multiply this one out to the c, and if you separate this one, let me separate it like this. C is out there actually, a to b, ay, g rho, ay, and dy. And y is multiplied in here, distributed, and then it's ab, g rho, ay, y out there, and dy. So if you distribute this ay here and there and rewrite it, it looks like this. And you can see this integral is multiplied to here and there, and you can see the c times this one and c times that one shows up. So they cancel. And you're left with y star times this one and this one inverses. So from here, by setting these two things equal to each other, that was the idea, that you get the following. Y star in the left-hand side from a to b, and g rho is a constant, they all cancel. Let me write it like this so that you can see it clearly. Dy, that's left-hand side. After you cancel negative, you have a to b, g rho, ay, y, dy. That's the right-hand side, the earlier work calculation. So we're wondering what would be the location of this ball so that lifting that heavier thing into this distance is the same work as the lifting this whole thing by slice. So that location y star is the following. AB and g rho cancels. So here's the y times ay, rearranging the earlier one, divided by a to b, ay, and dy. All right, we know ay formula of ay. Y is just a variable, so we can definitely calculate this, right? Does that make sense? So if y star, if you put that heavy ball in that location y star, which is given by this formula, the work lifting this one to that stage, or lifting this one slice by slice all the way up to there, is exactly the same, right? So do anybody recognize this formula here? This is called center of mass. The center of mass becomes a very, very important formula of the idea and the notion in physics. Okay? If there's a center of mass in there, if you want to replace this entire body rigid motion with a point mass, that's what they call, the y location must be calculated like this. But we don't know exactly what is the x location or that, but then you have to do the different slicing. It's slicing due to this across y-axis. You can slice it like this, and changing this to ax and ax in that, then it gives you, x location, and then it pinpoints one point in that solid that you can replace with a point mass in there, so that universal gravitation also applies there to that point mass. Okay. Turns out it's a very important notion. Good. I did it. 10 minutes. All right, this is called the center of mass. When in the physics, they start with the particle version, they introduce one version and they quickly jump to this integral version, but it seems like a nice way to relate the continuous version of a center of mass, and the one way to understand. But there are several other versions to derive the center of the same notion, and center of mass rises from other physical comparison and phenomenon.